which I think we are. So please take it away, Yoshi.
Yeah, okay. Can you hear me? Sorry.
Yes.
Okay, that's good.
Please take it.
Can you share my screen?
Absolutely.
Okay. Then, so if you're okay, so we'd like to start.
Please go ahead, Yoshi.
Yeah, sorry. Maybe the mic. Okay. Can you see my screen?
Yes.
Okay. Thank you very much. Thank you very much, everybody. So, my name is Miyoshi from the Nagoya University. Today, we are going to talk about the report, our is the BJ. ECPJ is the Beijing. So we have organized the workshop, the Beijing, the end of the July. And the title of this workshop, the current understanding of the geospace environment variations based on the multi-spacecraft observation during the solar cycle 24 and 25. So the combinates include me and Kanako Seki, the University of Tokyo, and Professor Zong, the Peking University, and Sasha Wen and Yanis Douglas, and the Professor Chen from the Nanjing University. So here is the scope and goal of this workshop. So right now, the many mission provides the very wonderful result for the Barren probe and TEMIS and MMS, the Elfin, and other satellites, and the Japanese Arase satellite, and ESA cluster satellite, and the various ground-based observation. And we'd like to share the new results from the new mission. And also we'd like to run the new insights from the simulation and integrated study. So now the scope of this workshop. So we'd like to summarize the research on understanding and forecasting the dynamic process, the phenomena in geospace based on the observation, the theory, and modeling during this solar cycle and cycle 24. And we'd like to overview the latest discovery, the current scientific understanding on the geospace to establish the state-of-the-art concept for the geospace. And the theory and the model will be summarized and reviewed critically according to their ability to address the observed phenomena. So actually we proposed the original the workshop during just before the pandemic, but actually during the challenging the period, pretty difficult to organize this workshop. But last July, we have a chance to organize this workshop. So this is the group photo, and about 60 participants that joined the workshop, and we enjoyed the whole week the workshop in the Beijing. So here is the organized session for this workshop. The session one is the cold plasma dynamics, led by the Naomi Maruyama-san. And session two, the focus is the warm and hot plasma dynamics, organized by the Yanis Douglas. And the session three, the radiation belt dynamics, organized by Wen. And the session four, the current system, organized by the Yusuke Ibihara-san. And session five is the generation and propagation of the various magnetic waves organized by the Kanako section. And session six, the cross-digital coupling, organized by Toshi. And session seven, the cross-energy and cross-scale couplings, organized by Qinanli. And session eight, the storm-substance relationship, organized by Professor Zong. And also that we have the special session about the solar physics, organized by the Professor Chen, the Nanjing University. So after my introduction, so the colleagues will briefly summarize the topics and discussions at each session. But here I'd like to briefly mention about only the small portion of the topics in the meeting. So the cold plasma dynamics session that we have discussed the various topics and including the erosion, the rippling of the plasma sphere, the surface wave, and atmospheric escape. And in the session for the warm and hot plasma dynamics, that we have discussed the oxygen torus and warm plasma cloak and oxygen-rich situations. On radiation-based dynamics that we have discussed wave-particle interaction, including both the quadrilinear, the nonlinear stuff, and also discussed the global impacts on the nonlinear wave-particle interaction. And besides the torus, the heat, and the EMIC waves, we have also discussed the kinetics, the RBM waves that contact with the pitch angle scattering and radial diffusion. In the session for the current system, so that we discussed the origin field line current, and substone current weight, and wavelets, and cross-scale the coupling processes. In session 5, we have discussed the generation and propagation of the various magnetosphere waves, including the nonlinear wave-particle interaction for both the torus wave and the ULA fast-moving waves, and the importance of the duct to guide waves along the field line. And the session 6 that we discussed the tail in the magnetosphere, the thermosphere coupling processes, and atmosphere, thermosphere, magnetosphere, the coupling processes. And session 7 that we discussed the cold plasma, the radiation-based coupling, and the MSW wave and the EMIC wave couplings, other coupling processes. And the storm-substorm relationship session that we discussed the importance of the mesoscale injection, solar wind driver, super substorm, and importance of the oxygen, the ion, to develop the large magnetic storms. Okay, and today, the Naomi, Toshi, and Qinanli review the organized session. So after me, the Naomi is going to talk about the cold plasma dynamics, and then the Toshi talk about cross-regional coupling session, and finally the Qinanli, give a review and report about the cross energy and the cross coupling the session. Okay, so maybe the Naomi, so can you share your screen?
Yes, I'm coming.
All right.
Yes.
That sounds good. And as Yoshi suggested, that perhaps that we will be asking questions after each
Yes,
speaker. So if you have any comments or questions, just raise your hand or unmute yourself and speak up. Either or is fine. Please,
Sounds-
take it away. Yeah.
Sounds good. Thank you. Can you hear me? Okay.
Yes.
Okay, that's great. Okay. Okay. Yes. Thank you very much for the introduction by Miyoshi-san. And hello, everyone. I'm Naomi Maruyama from University of Colorado, LASP. I would like to report on the cold plasma dynamics session. So here is the outline. First, I will briefly give the overview of the cold plasma dynamics session. And next, I will highlight the two topics. First is plasma pores, surface waves, and the second highlight is on the oxygen torus and warm plasma clock. And then I will summarize the outstanding questions. Miyoshi-san didn't mention that, but actually before the workshop, all the speakers were asked to bring outstanding questions to bring to their talks. And all the speakers did a great job of identifying excellent questions. But then, so how do we address these proposed outstanding questions? And I will conclude the talk by emphasizing the critical need for future multi-spacecraft missions. So in our session, cold plasma definitions have been broadened from pure plasmasphere to cold plasmasphere in the magnetosphere in general. The topics presented address cross-energy interactions, magnetosphere-ionosphere coupling, and the critical role of the ionosphere originating cold plasma in the magnetosphere. I'm not sure if you can see this, but Dr. Fei He from China talked about the newly discovered plasma pulse surface wave. And Dr. Masahito Nose from Japan presented the oxygen torus and warm plasma clock. And Dr. Zhenpen Su from China discussed how to infer the oxygen torus from emic waves. And Dr. Xinyan Chu from US talked about the new science revealed by machine learning models. And lastly, Dr. Elena Kronberg from Germany presented the cold ion outflow. The first topic of our highlight is plasma pulse surface wave, which was discovered by taking advantage of the multi-spacecraft observations using Van and probe and ERG or ARASE and DMSP. So what is plasma pulse surface waves? It is identified as a sawtooth-shaped plasma pulse undulation in the afternoon and dusk sectors, which was observed by Van and probe, shown by here. Previous MHD theory, Chen and Hasegawa et al. Predicted that pressure pulse acting on the steep boundary of the plasma pulse surface may excite the discrete eigenmode of the plasma pulse surface wave. However, there was no observational evidence before. At the same time, DMSP observed the sawtooth-shaped large-scale undulations along the equatorward edge of the diffuse auroral precipitation, which matched to the plasma pulse undulation when mapped to the magnetospheric equatorial plane that is shown by this white line here. The sawtooth aurora observed by DMSP in both hemispheres, this is northern hemisphere and this is southern hemisphere, is an optical manifestation of the plasma pulse surface wave. The undulation features shown here are propagating sunward or westward by 0.01 degrees per second with wavelengths of 6.4 to 10.2 degrees in azimuthal direction. Dr. Fei He and his group studied the statistical properties and their connections to auroral signatures. First, giant undulation usually occur within the 4 hours following the beginning of the storm main phase and finish within the 4 hours around the storm peak. Secondly, the anti-sunward edge of the giant undulation is quasi-stable, between 18 to 19 MLT hours during their lifetime. This feature indicates that storm time injections might excite plasma pulse surface wave at the quasi-fixed location because particle injections, especially ion injections, are most likely the driver of the plasma pulse surface waves. The second topic of our highlight is oxygen torus and warm plasma clock. For those of you who are not familiar with the topic, oxygen torus is identified as the enhanced flux of low energy few eV to 10 eV oxygen single plus and double plus ions near the light ion plasma pulse, peaking from L equals 3 to 5. As the name torus indicates, it was considered to be a ring circling around the Earth like a donut. And however, oxygen torus turned out to have crescent shape thanks to multi-spacecraft observation using Van probe, shown by red, Arase, shown by green, which identified the MLT extent of the oxygen torus. Statistical study shows that oxygen enhancement is frequently observed in the night side and dawn MLT sectors. Furthermore, new studies suggested new mechanism. Low energy oxygen ion is loaded from the night side oral ionosphere, and Van probe observed the field-aligned oxygen near the local midnight in the inner magnetosphere, and then the low energy oxygen drifted eastward to form the crescent shape. So one of the unsolved questions is, how does oxygen torus relate to warm plasma clock? Warm plasma clock is located in the plasma trough, distributed from night side to the morning side, extending to higher L values. Oxygen ion and light ions have similar distributions. So what is the relationship between the oxygen torus and warm plasma clock? Are they different phenomenon? Or are they the same thing viewed from two different perspectives? For example, warm plasma clock have higher energy, from 10 to 100 eV or higher as compared to few eV to 10 eV of oxygen torus. Additionally, warm plasma clock is located outside of the oxygen torus, which is warm plasma clock is 5 to 10 RE to 7 to 12 RE in the morning side, whereas oxygen torus is only from 3 to 5 RE. So how do their ion compositions differ? And this is critical for quantifying the ion, mass and ion composition in the magnetosphere because they impact the ULF and EMIC waves, as Dr. Shen-Pen Su presented in our session. Here is a summary of the outstanding questions suggested by the speakers. What are the roles of the plasmasphere storing cold plasma and recirculating into the plasma sheet and ring current sources? What are the characteristics of the newly discovered plasma pod surface waves and their connections to oral precipitations? What are the characteristics of the oxygen torus and warm plasma clock, and what is their mutual relationship, as I discussed earlier? How do EMIC wave characteristics depend on the cold ion compositions? What are the characteristics of the spatial and temporal evolution of the plasmaspheric dynamics, such as plasmaspheric erosion and refilling? And lastly, what factors drive the ion outflow? And what is the role of the outflow to the total atmospheric escape, which is very important for planetary habitability? So how do we address all these outstanding questions? We need future multi-spacecraft missions. Here is the list of missions we discussed during our session. And today I would like to highlight the mission that is less familiar to US audience. The first one, SMILE and Fyungun and Kyeokyo 2. I'm sorry for my mispronunciation. In his talk, Dr. Fei He pointed out the exciting opportunities and the challenges of global imaging network. I'm sure you all know SMILE mission, which is expected to launch next year. It's a joint ESA and Chinese mission to study the solar wind and magnetosphere interactions by globally observing the X-ray emissions emitted when the solar wind particles interact with the neutral particles in the Earth's upper atmosphere, as well as the global auroral imaging in the ultraviolet. At the same time, China has Pyongyang satellite auroral imaging with both high resolution and wide field auroral imager from a low Earth orbit. And lastly, it's hidden here. Two mission was launched in March 2024 to an elliptical frozen orbit around the moon. Maybe I can move it. Okay, here. Okay. To support the communications from the far side of the moon and the lunar south pole, which is carrying the plasmaspheric imaging, extreme ultraviolet camera, ionospheric outflow imaging, and ENA imaging. Excuse me. As you may have heard, the pilot mission was suggested by Dr. David Malaspina, and the mission concept study combines equatorial radio tomographic imaging with meridional EUV imaging and in situ observations to trace the flow of mass and energy through the coupled geospace system. And lastly, as you may have heard also, the EPIC missions have been proposed by Dr. Jerry Goldstein. In conclusion, we need more multi-spacecraft missions to study cold plasma, taking advantage of the global collaborations. Thank you very much. Any questions?
Thank you, Naomi. Questions? Comments?
I have a comment.
Go ahead, Richard.
So, Kazui Takahashi is about to submit a paper studying the time dependence of the oxygen during magnetic storms.
This one?
And yeah, and he finds that although the average ion mass always peaks at morning local time, the oxygen itself is only peaked there during the storm main phase. And after that, it seems that it's more symmetrically located around the Earth. So from that perspective, it might be that a cloak-like structure might evolve into a torus-like structure during a storm.
Oh, thank you very much. Yeah, we are looking forward to this new publication to further understanding this torus and warm clock. Thank you.
You're welcome. Thank you for your talk.
Thank you.
Richard. More comments or questions? All right. Thank you.
Thank you.
Okay, so the next is the Toshi.
Yep.
Sorry, I have to disconnect.
Okay, thank you very much, Maruyama-san.
Okay, so following up, I'm gonna briefly describe what the cross-scale coupling process chapter will look like. And here's a list of presenters who came to the meeting and discussed the ideas about the current status and challenges of the topic. Some of them are invited, others have generously stepped up and contribute. As a name stand, this is a pretty broad chapter, hence it's pretty challenging to summarize the status of the community, but and we really don't mean to be super comprehensive about everything, as well it's going to be just a whole separate book. But we looked at the expertise in the team and try to distribute efforts so that we can provide balanced coverage. So here I'd like to give some overview of the chapter structure and what kind of basic concepts and questions we will address. So we'll start off by providing an overview of what we mean by cross-regional coupling processes, what we know, what are the challenges. So, here are some illustrations that attempt to summarize what kind of processes are important when we talk about solar wind magnetosphere ionosphere coupling, tailwind magnetosphere coupling, or ionosphere thermosphere coupling. So the solar wind create a transient when the solar wind enters the bow shock and magnetosheath, and then the magnetopause. Like foreshock transient, magnetosheath jets, reconnection can also create some spontaneous flow enhancements. Those things do affect ionosphere magnetosphere system, like driving ULF waves, creating fair and current system, and polar moving over forms, etc. So those things should be introduced. I will provide some illustrations and history about such the research of such processes. And then in the magnetosphere, we have the ring current, region 2 current system, and the feedback from the ionosphere that creates a strong westward drift known as SAPS. We also have the dawn-style counterpart towards things near the polar cap boundary. There are a lot of small-scale and mesoscale flow channels and related plasma transport like Broom that Naomi has just talked about. And going further down tail, the magnetotail reconnection is an important contributor for creating the transient processes in the night side. And they create particle injection, dipolarization fronts, and they reach the inner magnetosphere and also impose current and precipitation structures to the ionosphere. The bottom two panels summarize major mesoscale structures that contribute to the energy and momentum transfer between the regions from the cusp to the night side or oval, and then to the night side or oval to the suborbital ionosphere. Then they, of course, vary between quiet time and active time. So there are a lot of grounds to cover. That from ground-based measurements and also numerical simulation, there have been a lot of effort understanding how we characterize them and how they impact energy transfer between regions. So in the following chapters, we'll talk about more specifics and two interconnected regions and how coupling process work. So for example, the magnetosphere and ionosphere. From the global point of view, the major challenge is the state specification, such as fair and current, precipitation / conductance, convection, and also Poynting flux. So they come into this famous Ohm's law. If we consider the electrostatic situation, of course, we need to think about the electromagnetic coupling too. That's another challenge. But still in this simple state specification, we need to know what each parameters evolve. But surprisingly, this is very challenging. Each type of measurement have different spatial and temporal resolutions. So some instruments can perform better than the other. So when we have to stitch them together, there are always some sort of inconsistency, like the Poynting flux pattern doesn't agree, depending on what kind of data set used. So those are going to be major issues to be discussed. But first, we will provide the basic understanding of how the global the states will look like. And then the other important perspective is a more mesoscale and transient energy input from the magnetosphere and feedback from the ionosphere to the magnetosphere. With a recent development with local high-resolution imaging, for example, we can see individual arc scale precipitation over discrete or arc. See here pulsating aurora, so wave particle contraction creating dynamic evolution of precipitation. Those information can be taken to infer the conductance or precipitating energy flux and characteristic energy. There have been a lot of techniques developed in the community about that. So understanding of how much such mesoscale structures contribute to the total precipitation or total plasma transfer. Those are very important for quantifying the importance of the multi-scale processes. Another important issue is a high energy precipitation. So optical instruments can only provide precipitation up to a few tens of keV, but it is known that there are precipitations up to MeV or multi-MeV energy range. How much they really contribute to total conductance and also the atmospheric chemistry is not very well known, and was very hard to characterize. But there have been some efforts in the community using the modeling and precipitation and also the chemistry. So those things are also important to be covered because this is about precipitation. So this section should coordinate a lot with the wave and radiation belt chapters. Next up, so Arwayne and Magnetosphere coupling is another pair of important coupling regions. In addition to the large-scale solar wind, solar wind can also create transient through the interaction between solar wind and the magnetosphere. There are many things discovered in the last few decades. Some of them are summarized here. And those have been demonstrated to impact ULF waves, or particle precipitation, and transient connection, and so on. So they are already known to be very geoeffective. However, those are also harder to measure. They are short lasting. They are localized. So if the satellites are not in the right place, we can't really see them. But there have been a lot of good statistical studies that quantify the distribution occurrence rate and under what conditions they become geoeffective. So those things should be summarized and discussed so that the broader community can understand how we should understand the coupling from the solar wind to the magnetosphere, including such transients. Moving on to high latitude, the polar cap is generally an open field region without too much high energy precipitation, but still there are a lot of interesting processes going on. For example, polar cap arcs and patches, polar rain, and those things. And the other important thing is the space hurricane that Qinanli and group has recently worked on. So those things are related to the small scale flow shear structures in the polar cap. And recently, it's been shown that they create an enormous amount of heating. So there's a large energy input, even under northward IMF. Those have been poorly known in the past. So those are important recent findings. And they seem to be involved in the large-scale plasma transports. We should place these transients into context so that we can understand what their roles are. Under southward IMF, the plasmaspheric plume goes into the open field lines. Sometimes they make the way to an outside or oval, affecting the plasma density structures there. And then some of them can even return to the day side. So there's a global plasma circulation going on. And some of those are related to fast flow channels, impacting the nicer reconnection and also the substorm activity. So it's not just passive cold plasma floating around, but they are part of the active MI coupling processes. So they're important to be covered in the cross-scale perspective. The further down the tail, there are, of course, important processes such as current sheet formation, reconnection, and then Bercy-Bark flows injection, depolarization fronts. Those have been discussed quite a bit. So the injection have been shown to be important for providing safe operation for the radiation belt. So understanding how the tail behaves, how reconnection, synchronicity, those things react to the solar wind, how much particle acceleration can occur, what kind of current system will take place. Those things are all important in terms of global coupling processes. Current sheet flapping is another specific phenomenon of interest. So there have been there's lots of studies about how they look like. Some of them can be seen in the ionosphere as modulation of the overall structures. They indicate fundamental features of the plasma instability, like KH. So those are also important regions in terms of plasma physics. The last portion is about the coupling in the ionosphere and thermosphere. There have been a lot of good large satellite measurements showing the transient structure in the ionosphere, not only just highlight tube, but also in the equatorial region as well. So those the statistical studies about density irregularities, fast flow, scintillation, and so on, those will be covered in this chapter. Then lastly, the coupling to the thermosphere. So this is probably one of the most challenging part. The neutral measurements are very lacking, but as I mentioned earlier, they are important for describing the precipitation, conductance, so those coupling parameters between the ionosphere and magnetosphere. So there have been good modeling efforts going on in the community, like Gatum, TaiGC, and so on. And they have made good summaries about how the energy flows between regions, between processes. So those summaries will be provided. And also even coupling down to the mesosphere in terms of composition change like ozone destruction. So those things have space weather impact. So although these things are challenging, we attempt to cover those important regions as a kind of closure to the whole coupling processes between regions in geospace. So in summary, what we are thinking about is to provide overall introduction, and then MI coupling, including solar wind, biosphere coupling, then coupling around the tail, and coupling in the ionosphere thermosphere system. So these things we think will provide a good portion, if not all, about the cross-scale regional coupling, summarizing the importance of why we need to discuss mass energy momentum transfer between the region, not just in one region. So that's the basic idea for this chapter.
Thank you, Toshi. Do we have comments or questions for Toshi? Oh, thank you, Toshi. Let's move on. Qinanli.
Next is the Qinanli.
Yes, let me share my screen.
Yes.
Okay, it's great to see everyone today. So I am Qinanli Ma. I will be covering the cross energy chapter for Miyoshi's book. So I will acknowledge the future courses for my book chapter, and they are listed here. So in this I should have put full screen. In this presentation, I will mainly talk about the cross energy coupling of particle distributions through resonant interactions with the plasma waves in the magnetosphere. Although we in the meetings we also discussed the other methods for the cross energy coupling, like the Coulomb scattering and the charge exchange. But in this presentation, I will just focus on the waves, and we will cover the other topics in the book chapter in the future. So this is the outline of the several aspects that I will present today. So the first one is the coupling of different electron populations through the Wismor waves. And the second one is the coupling of ion populations through the EMIC and magnetosonic waves. The third one is the UF wave modulation for the different particle populations or the different wave modes. And the last one is the impacts of the very low energy cold reaction, the density on the waves and high energy populations. And the last point is the outstanding questions. Yeah. So here shows in this plot, here shows the reaction flux measurements by the one poles as function of the L shell and the time for different energies. And as we can see, the reaction variations is very different from the low energy reactions to the high energy reactions. The low energy reactions typically show the typical very quick and fast transient variations, and those may be related to the injections. But as the energy goes higher and higher, the reaction population seems to be more diffuse-like, and the time scale of variations seems to be longer. So those variations are very different across the energies, but the basic question is, are they affected by through some methods by one population to the other populations, and whether they are coupled? And then actually, this question has been quickly understood soon after the launch of the one poles. Here is one example. This is a cartoon by Yoshi paper in 2013. So during the quiet times, the plasma pulse is expanded, and the reaction fluxes in the reading belts are very low. And but during the disturbed times, the plasma pulse is eroded to low L shells, and the reaction injections from the plasma sheet can be transported to the inner sphere, and those reaction injections generate the cross waves. And then the cross waves can accelerate the C reactions from 100 keV up to several MeV energies. And those can even produce the peak of the reaction phase space density in the heart of the reading belt. And this is also observed by the one poles and also modeled through the quasi-linear modelings. Indeed, there are many modeling efforts and comparisons with the observations to support those cross energy couplings of the reactions through the cross waves. Here is one example. This is the reaction phase space density distribution function observed by SEMIs. We can see that the reactions during the injections has high phase space densities at the 30-degree pitch angles and lower phase space density at 0 or 180-degree pitch angles. And those reactions may generate cross waves. And the cross wave generations, the cross wave energy gain is plotted as function of the lateral in this panel for different wave frequencies. Using the quarter ray simulation results, they also have demonstrated that the cross waves can be generated by the observed reaction distributions. After the cross wave generation, the cross waves can indeed accelerate the reactions. And here is again the figure from Yoshi paper, and here shows the phase space density as function of the time. So in several hours of time, the reaction phase space density increases as for different energies, and there is a time delay from the low energy reaction oscillation to the high energy reaction oscillation. And then this is very consistent with the one pulse observations. So this demonstrates that the reaction injection energy can be transformed to the cross wave energy, and then the cross waves can provide the oscillation energy for the relativistic reactions populations at up to 7 MeV energies. And in addition to this cross energy transfer, there is also another transfer of the cross waves. That is that the cross waves can also build a source for the heat waves. And this is the retracing results by Jacob Bartolink, and the cross waves launched at the outside of the plasma pulse can be traced to be reflected into the Plasmasphere, and it's also maybe a source of the heat waves, especially at high L shells. And then the heat waves can cause the decay of reactions. There are many modeling results for the impacts of the heat waves for the energetic reaction populations. And here is one example. Heat wave, the statistical heat wave amplitude is plotted as function of MLT and time in this panel. And the next panel shows the model of the reaction flux as function of the energy and the time during the recovery phase of one storm, and we can see the reaction flux decays due to the pitch angle scattering by heat waves. So this demonstrates that the reaction injections outside plasma pulse can lead to the actually long-term decay of the energetic reaction fluxes inside the plasma pulse. And the immigrant, the protons at different energies can also be coupled through the interactions with the immigrants or Magnetosphere waves. There are also many observation and modeling efforts to demonstrate this energy transfer. So this here shows one example of the coupling of protons at different energies through Magnetosphere waves. The reincarnated proton is shown in this panel. Here shows the pitch angle distribution of 5.3 keV protons. And the first panel shows the plasma density. So the reincarnated protons with positive gradients of phase space density can generate the Magnetosphere waves. And the Magnetosphere waves is indeed observed at the inner edge of the reincarnated proton populations. And then at the same time, we also see the enhancement of protons at 113 eV energy, and especially at 90-degree pitch angles. And then those protons appear at the same time when we observe the Magnetosphere waves. So this there are also many events, similar events observed by one POPs and other satellite regions. So this may indicate that the reincarnated protons can excite the Magnetosphere waves, and then the Magnetosphere waves can hit the low energy protons at about 100 eV energy. There are also observational evidence for the cross-energy coupling of heavier ions through the interaction with the EV waves. Here shows the one example for the hydrogen band EV waves interaction with the helium ions. Here again, the reincarnated protons are observed here, and at the inner edge of the plasma, at the outer edge of the Plasmasphere, we also observe the hydrogen band impulse here at the frequency above the helium gel frequency, and at the same time we also observe the perpendicular heating of the heliums at the 453 eV energy. So this also may suggest that the reincarnated protons may generate the EV waves, and then the EV waves may hit the low energy protons at 453 eV. Then another aspect of the cross energy and cross energy coupling is through the RF wave modulations. The RF waves can cause the simultaneous modulation for the particle populations at different energies, as well as the wave modes. Here shows two examples of the previous studies. So here the first panel shows the RF waves as the wave compression of magnetic fields are just shown in the black line. And the wave seems to be modulating the reaction fluxes. Here shows the reaction flux as function of the pitch angle. And what is more important is that the waves can modulate the anisotropy of the reaction fluxes. So here shows the reaction anisotropy as function of the energy at time. During this magnetic field minimum, we can see the reaction anisotropy increases. And this increase is also at the same time when the authors observe the crosswave excitations here. So this indicates that the crosswave excitation is caused by the anisotropy reaction fluxes, and those reaction fluxes are actually modulated by the UF waves. And what is also more interesting is that the authors also observe the enhancement of ECH waves at the same time with only when they observe the UF modulations. And the ECH waves may be generated through the loss cone instabilities. The reactions with enhanced anisotropy distributions may cause the more significant loss cone distributions, and those may also generate the simultaneous cross waves as well as the ECH waves in this event. There are also some UF wave modulations of the proton of the ions through the interaction with the EMI waves and through the interaction with the EMI waves. Here shows the one example. Here in this paper, the authors calculated the energy gain of the ions due to the interaction with the UF waves as shown in this white black line. And those black lines match very well with the observed ion energy spectrums. So this indicates that the observed elevated energy temperature is actually caused by the oscillations due to UF wave electric fields. And there at the same time, they also analyze the waveform for the UF waves and observe also a smaller, shorter time scale structures. And when they also zoom in into a shorter time period, they identify those waves as immigrant frequency ranges. And those immigrants in a shorter time scale is actually modulating the ion fluxes at an energy from 10 eV up to 100 eV. They also performed some theoretical analysis to demonstrate that the appearance of the ion fluxes at those energies may be due to the reaction and heating by the immigrants observed during this period. So this event demonstrates that the UF waves and as well as the immigrants can cause the modulations of the ions across different energies. And the final aspect is the importance of the reaction density. Actually, the core reaction density at very low energies can modulate both the plasma waves and the high energy particles. Here show two examples for the modulations of the waves by the cold reaction densities. In the left-hand side panel, they also have shown the density in the first panel and the cross waves at the second panel. During the at the cross waves, the peak of the cross wave amplitudes are observed just near the peak of the reaction densities, and those reaction densities may modulate the cross waves, and those cross wave amplitudes are actually very high. The wave amplitudes are above 300 picotesla. And they also made statistical studies to indicate that those very high energy rhythm waves observed typically at high latitudes, and when they're also very well correlated with the density structures observed outside the Plasmasphere, and maybe more correctly identified as in the plumes, but those wave frequencies are in the cross wave frequency bands. And the right-hand side panel shows the variations of Magnetosphere waves and the image waves by the plasma density. And here shows the Magnetosphere waves observations, and here shows the image wave observations. They are clearly cut off by the density structures. When the densities are very low, the waves disappear, and when the densities are enhanced, the Magnetosphere waves appear, and the image waves may appear near the edge of the density enhancement here. And finally, the reaction densities may also modulate both the reaction precipitation as well as the reaction accelerations at high energies. Here is one example for the reaction precipitation modulated by the density. Here, the first panel shows the Plasmasphere density and the plasma shelf density and the plasma plane density structures. And those density structures may cause the vibrations of the heat waves in this event. The heat waves are observed in the Plasmasphere and as well as in the plumes. And the wave those heat wave amplitudes can be as high as 100 picotesla. And we did a collinear theory to calculate the precipitating energy flux for those events. And the final panel shows the model reaction precipitating energy fluxes as function of the energy and the time. So typically, the very high energy precipitations are modeled inside of the plumes, and those are actually affected by the plasma density at very low energies. So those low energy density variations can cause the several keV to up to several hundred keV reaction precipitations to the atmosphere. And the low energy reactions are also very important for the very high energy reaction oscillations. Here is one example. In this paper, the authors have shown that although the oscillations at 1.8 MeV reactions appear very often, but the oscillations at 7.7 MeV is not that often. And the authors analyzed the background conditions and suggest that the oscillations of 7.7 MeV reactions requires not only the geomagnetic activities, but also very low density especially at the low L shells. Here, the third panel shows the density was observed by the Maruyama probes, and we can see that only when the density is loaded to the low L shells and during the disturb times, then the oscillations of 7.7 MeV appears here. So here are the outstanding questions we listed during our workshop. I just listed the three major questions. The first one is how does the cross energy interactions change the entire particle populations distribution functions? So typically we observe Maxwellian distribution functions, kappa distributions, power law, and the Palmer-Hintel distribution functions as function of the energy. And those observed energy spectrums may be the consequence of the cross energy interactions. So we may need the cross energy modeling to fully explain the energy spectrums observed by Maruyama probes. And the second question is, what is the energy budget for the different particle populations during the cross energy interactions, and how can we quantify the energy flow? We talk about the energy flows from the inertial injections to the wisdom waves and to the electric electrons, as well as the energy flow from the weak current ions to the emitter and the magnetic waves and the superthermal ions and energetic electrons. So what is and how much energy is actually transferred from one population to the other population, and how to quantify them are still not very known. And the third question is how can we model the cross energy interactions in a self-consistent way involving multiple particle populations? So we may need the self-consistent modeling to consider all of those processes from the injection to the wave generation and the particle precipitation, as well as the oscillation processes. And typically, when we perform the linear modeling, we just focus on one process. But in the future, we may need to consider multiple processes and perform a self-consistent modeling. And to do that, we may also need to include the realistic density structures because they may be important for both the precipitation and the particle oscillations. And that is the summary of our focus group, our workshop activities, and I'm open to questions.
Thank you, Qinanli. Do we have comments or questions? Great, maybe not. Thank you. Thanks a lot again. Yoshi?
No, thank you very much. So now we are preparing the review books, Ishi book series. So your comments and feedback are very welcome for us. But anyhow, thank you very much. Thank you.
So when do you think the book will be, the monograph will be ready for publication?
Maybe next year, hopefully the next year.
Yeah, so in about a year, so we should be expecting it. Thank you. Thanks again to all the speakers and to Yoshi and Wen who organized the seminar. And I hope that we will see many of you at the upcoming HU meeting. And please stay tuned for the announcement of the subsequent seminars. Thank you and have a great weekend.
Very much.
Thanks.